Okay, so this is just jumping off from our last video on endothermic and exothermic reactions. So a thermochemical equation is just a balanced chemical equation that's showing the energy change. Now we've just done an example of a reaction, so I'm just going to quickly scroll up to show you what that reaction was. So this was our particular reaction here. So we burned propene in the presence of oxygen to form carbon dioxide and water. So when we did that, we had an energy release of negative 6,822 kilojoules. So I'm just going to write that information down here. So 2 lots of C3H6, so that's our propene, and that's a gas, plus 3 lots of oxygen gas, and that's going to form 6 lots of carbon dioxide gas and 6 lots of water. And I'm assuming this is in the gaseous state because this is a highly energetic system. And so the last thing I'm going to do to make this a thermochemical equation is I'm just going to add the change in enthalpy. And I've sort of run out of space. One second, I'm just going to scroll over. And that is going to be negative 6,822 kilojoules. Okay, so that's all I need to do to make it a thermochemical reaction is to determine the amount of energy and then just pop that on the end there. So just like what they've done here. Okay, so something really important to know. If we double the amount of products and reactants, then the energy required is going to double as well. So everything is proportionate. So if I was to take my example from here, this previous one, and I was to say, actually, I've only got 1 mole of this substance, I've got 1.5 moles of this substance, I've got 3 moles of this and 3 moles of this, then my energy balance would have to halve as well. So Hess's law states that the enthalpy change for the overall reaction is equal to the sum of the individual steps. Okay? So sometimes what happens is we don't have that straightforward reaction where one thing breaks off and then attaches to another and then that's it. We have like steps within a reaction. So a really good example of this is something burning in the presence of oxygen, because usually what happens is when you burn stuff like wood, I mean, yes, the flame is hot, but it's not hot enough to get a complete burn. And what you'll see left over is you'll see a lot of ash left over. Now, if that had a complete burn, or coal even, if that had a complete burn, then you wouldn't see any of that ash or that coal or anything like that. You would just see nothing because every single bit of that wood would have been turned into carbon dioxide. But that doesn't always happen. We get these kind of intermediate products. So that's why it's really important to use the individual steps to actually calculate the total enthalpy change, because we want to get those the entire reaction energy included. Whew, that was a mouthful. So just as a quick example here, so if I was burning something like wood, if it was to partially burn, it would only form carbon dioxide, and then to complete the burn, it would have to form carbon dioxide. And so we start off with this first little half step here. So carbon and half of this oxygen molecule form carbon monoxide. So that bond, or that oxygen, the other oxygen is sort of just floating around in space like a little free radical chilling. And then it gets mopped up by the other side of this carbon here to form carbon dioxide. So this first step releases 110.5 kilojoules per mole, and the second step releases 283 kilojoules per mole. And again, if we were to double the amount of carbon or oxygen that was involved in the reaction, then we'd also have to double this energy value as well. So the total energy required for this reaction is going to be negative 393.5 kilojoules per mole. Okay, so let's have a go at some of these questions here. So I'm just going to select this and make this a little bit bigger. Some of these we've actually already gone through. So question 3 we actually went through in the previous video if you want to go back and have a look at that one. So going through, I want you to explain what enthalpy is. And again, if you want to, you can go back and revisit my last video. I want you to contrast what an exothermic and an endothermic reaction is. So again, go back, check out my last video. I think that video will be really helpful for you. What I wanted to do for you though is I want to have a go at the thermochemical equations for the combustions of just one of these examples. So I'm just going to have a look at methane. So if you're not sure what the chemical structures of these compounds look like, I would actually suggest going online and just having a look. I know the structure of methane is a really simple one though. because it's the most basic hydrocarbon, methane. And so that's going to react in the presence of oxygen, and that's going to form carbon dioxide and water. So if you want to have a go at this, you can pause the video now. And what I'm going to do is I'm actually going to pop up the balance equation on the screen, as well as all of their individual bond enthalpies from that table that we were using in the last video. So what I've done is I've gone ahead and I've calculated the individual bond enthalpies for each of these. So I'll just scroll up and I'll just show you now. So what I did is, this is in chapter 9.2 of your textbook on page 203, this particular table. So what I did was I looked at the types of bonds that I had. So for methane, we have 4 lots of this CH bond here. And then I looked at the same thing for oxygen gas. Now, oxygen gas is double bonded, so that's how I found the bond enthalpy for oxygen gas. The other one that I had was carbon dioxide. Now, carbon dioxide has 2 of these C double bonded to an oxygen, so 2 lots of this bond energy here. And then I did the same thing for water. So water has 2 of these OH bonds. And so I've got 2 lots of that bond there. And so that's how I calculated the individual energies for each chemical species. And then what I did is I just used the mole to calculate the total amount of energy, because I've got 1 mole of this particular substance, and then I've got 2 moles of this particular substance. So in total, the energy involved was 2,652. Okay, so now I'm going to show you how to do the thermochemical equation part of it. So we're going to use this formula that we used in the previous video. So the change in enthalpy is going to be the energy in the bonds that have been broken, take away the energy that's formed. So for this particular case here, we're going to do 2,652 take away 3,460. So I'm just going to quickly pop that into my calculator. So 2,652 take away 3,460, and that's going to give me negative 808 kilojoules per mole, or per reaction that's occurring. So because this is negative, this implies that this is being released to the environment, and so therefore this is going to be an exothermic reaction. So what I'm going to do now is I'm just going to write it as a balanced thermochemical equation. So we're just going to make sure that we have all our states and stoichiometric ratios in there. So we're going to have CH4, which is a gas, plus 2 lots of oxygen gas. It's going to come together to form carbon dioxide gas and water vapor. So that's going to be a gas there. So in total, and I should have my little stoichiometric coefficient. And in total, this energy change is going to be equal to negative 808 kilojoules per mole. So again, if I was to double the amount of moles of this particular reaction, it's going to double the amount of energy that's being released to the environment. Alrighty, so I'm going to leave it there. Have a go at the next couple of questions and let me know how you go. And I will see you in the next video talking about specific heat capacity. Talk soon, guys. Bye.